Hello everyone. So first of all, I would like to thank organizer for providing me opportunity to present my work. I am Nikhil Malviya. I am a second year PhD student in mechanical engineering department at Indian Institute of Science, Bangalore. So today I will talk about my ongoing research work on phonon transport in ultra-high thermal conductivity material beyond relaxation time approximation. This work is funded by DST-SERV Research Grant and Prime Minister Research Fellowship. So in crystalline material, where we have periodic arrangement of atom, which can vibrate under application of heat or temperature, and normal mode of these vibrations are called phonons. These phonon are the main source of heat transport in materials like insulators and dielectrics. These during heat transport, these phonon may scatter among themselves or with boundaries and impurities and defects present in the crystal. Now, depending on the order of anharmonicity present in the crystal, we can have 3 phonon interaction, 4 phonon interaction, or higher phonon interactions also. In these anharmonicity driven phonon scattering, we can either, the colliding phonon may either conserve the total momentum. In this case, we call it as normal process, or the total momentum of colliding phonon may be dissipated. In that case, we call it as Umklapp process. So in real crystal, these phonon scattering results in heat resistance to heat flow. Interestingly, in absence of Umklapp scattering, the normal scattering, which conserves momentum, provides zero resistance to heat flow. But in presence of Umklapp scattering or any momentum dissipating scattering events, all scattering process provide resistance to heat flow. Now these phonon transport are generally governed by Boltzmann's transport equation for phonon, which is a semi-classical integral differential equation and has this form. Here the left-hand side is a differential where and it is taken from Boltzmann's transport equations for gases, which is classically derived, while the right-hand term, which is a collision integral, which is integral over first Blown zone, and it is derived from quantum concept of Fermi's golden rule. Here there is n lambda. This is the phonon distributions corresponding to lambda, and lambda is the combined notation for phonon wave vector q and polarization j. Nu is the phonon group velocity, and the Cn is the collision integral or collision matrix, and it has this form. Here this V represent the strength of scattering, and they are generally and these are modified Fourier transformed of third order potential derivative of crystal. Now to solve the Boltzmann's transport equation, we generally use the linearized form of this collision integral, where this phonon distributions is considered as a perturbation over the local equilibrium distribution, which is given by Bose-Einstein distribution. Now, even after linearization, this is computationally expensive to solve the Boltzmann transport equation, and it is due to intensive coupling between phonon at different states, here lambda and lambda prime, lambda double prime. So we need to computationally cheap solve the Boltzmann transport equation, we need some approximation method. And the most commonly used approximation method is the relaxation time approximation. Here the collision integral takes this form, and the tau here is the relaxation time, which is reciprocal of scattering rates. Here it is assumed that all phonons decays to local equilibrium, which is given by n naught, which is Bose-Einstein distribution. So all phonon, all n lambda will go decay into n lambda naught. So in this approximation, it does not distinguish between the process or the scattering event is normal or umclamp, or it dissipates momentum or it conserves momentum. So in this case, the total scattering rate is just sum of all scattering rates, the normal scattering rates which conserves the momentum, and the scattering rate corresponding to momentum dissipation scattering modes. So now for calculation of thermal conductivity, we have this formula, but under the relaxation time approximation, this C lambda is the heat capacity, and the lambda mean free part. Under this approximation, it takes this form where tau is the relaxation time and mu is the phonon group velocity. So here, with this approximation, we resolve the original Boltzmann transport equation into sets of uncoupled equation which are easy to solve. Now, so not to check the validity of this approximation, let us look into some materials. So here is a scattering rate plot for silicon. This is plotted for 17 Q grade in reciprocal space, and these calculations are done for at 300 Kelvin, and it is for silicon at this isotope concentration. So here we can see the blue color. These represent the scattering rate for corresponding to umclap scattering. The red one shows scattering rate corresponding to normal scattering, while the black one shows the total scattering rates. So for silicon, it comes out that the normal scattering and umclap scattering, these are comparable. So for such material where the normal scattering and umclap scattering are comparable, we check the thermal conductivity for silicon, and it comes out that the relaxation time approximation predicts well the thermal conductivity of silicon, and hence we can say this approximations work well for this material. But is it true for all materials? So let's look at some exceptional material which have high thermal conductivity. So here is a scattering rate plot for diamond. So here we see, so the color coding is same. So here the blue one shows the umclap scattering, the red one shows the normal scattering rates, the black ones are total scattering rates. These are at 300 Kelvin and naturally occurring diamond with this isotope concentration. So here we see these umclap scatterings are weak throughout the scattering space. So now let's see what's happened for such kind of material, what's the relaxation time approximations predict. So we saw that for diamond, the relaxation time approximation fails. It underpredicts the thermal conductivity. So for material where the umclap scattering are weak, the relaxation time approximation cannot be used to predict thermal conductivity. So what next? So for such material, we have another approximation techniques called Kelbay approximation, which was proposed by Professor Joseph Kelbay. And here the collision, he clearly distinguishes the scattering for scattering for normal and umclap or which conserves the momentum or dissipates the momentum. So the total scattering, the collision integral takes this form. Here, all the momentum dissipating scattering event takes this n lambda, which is phonon distribution, to equilibrium, local equilibrium phonon distribution, n lambda naught. While he introduced a new term called n lambda star, which is flowing equilibrium. So all momentum conserving events, or which includes the normal scattering. So it takes this phonon distribution to this the flowing equilibrium. So this is how he distinguishes the scattering corresponding to momentum conserving or momentum dissipating scattering event. So let's see what this predicts. So I use the same thing. I calculated the thermal conductivity with this approximation for diamond, and it comes out that this Kelbay approximations works well for diamond or material where we have umclap scattering weaker and normal scattering is strong, and where RTF fails. So now the main takeaway point from my talks are these phonon scatterings. These results in resistance to heat transport, and we can have the momentum conserving or momentum dissipating scattering events for materials which have the thermal conductivity low or medium. So there we can use relaxation time approximations, and where the umclamp and normal scattering rates are comparable. And for in ultra high thermal conductivity material, so the normal scattering which conserves the momentum are strong compared to the umclap scattering which dissipates the momentum. So in such material, the Kelbay approximations works well, and we can use it for such case. So that's all for now. Thanks for your attention, and I'm ready to take any questions.
Right, thank you. So we have time for questions.
Nice talk, thank you. I have a question. You find the RTA works quite well for silicon, but not for diamond.
Yes.
So can you trace back what is different between silicon and diamond, that it works for one and not for the other? I mean, you'll say it's because the umclap processes are more important for one than the other, but why is that? Is it something about the nature of the interatomic interactions? Is it something about the phonon dispersion? What is it that's different between them?
So,
do you understand my question?
Yeah, I understood. So you want me what's the basic difference physically? What's the difference between diamond and silicon? That's what you want. So for diamond, so one reason is the scattering events, the momentum conserving and momentum dissipating event in silicon are comparable, while for diamond it dissipates the momentum conserving process are strong. So what's happened if we have only, suppose we have only momentum conserving process in crystal, so we will have infinite thermal conductivity. Yeah. Now, no, they are different. So for diamond we have high, the matrix element are larger. So yeah, so in V process we have a delta functions over delta of lambda 1 and lambda plus lambda 1 plus lambda, or lambda plus lambda prime plus lambda double prime. So for umclamp process it will be non-zero. And
do you want to comment? You had a question or a comment? Okay.
So in V element we have a delta function. It has inside a delta function, delta of what? Yeah, to conserve momentum. No, energy conservation is here, this delta. So now the V element.
Perhaps we can discuss this later.
Yeah, sure.
Any other questions for the speaker? Yeah.
With this equation, I have a question. So this is PD with looks like with a very high nonlinearity in your collision matrix.
Yeah.
Hello. Yeah. So yeah, if you look at this partial differential equation, I see a very high nonlinearity in this collision matrix, right? So what what numerical scheme you use to solve this equation? How do you solve this equation?
So that's what I said. I first linearize this equation, and after linearization, I solve it. Means
Like what is the procedure you use to solve it? Like,
so when we have this linear equation, it just convert into the linear sets of equation which I can use.
When do you
means I am using conjugate gradient to solve this Boltzmann transport equation.
No, this is a
Like
partial
that
differential equation, right? So do you use any numerical technique like finite difference scheme or finite element scheme, or do you use any numerical discretization?
No, not that.
Okay, and what time marching scheme you use?
What?
So there is a time derivative, right? So what is the numerical scheme you employ to solve this equation?
So we take first the Fourier transform
Uh-huh.
and then we solve it.
So do it in Fourier basis, this one.
Yeah, in Fourier base.
Okay.
So the whatever solution I saw now, they are in under statics, static condition, not the
Oh, okay.
transient one.
Okay. Okay, thanks.
But we are working on transient Boltzmann transport equation.
Okay, any further questions for the speaker? If not, let's thank the speaker once again.